So before I made the video on Engel's theorem, I wanted to talk more about representations because the proof of Engel's theorem has some concepts about representations that we haven't talked about, and Humphreys actually doesn't mention in the book. And I found some lecture notes from MIT that I'll put in the description that goes into these concepts. So it explains exactly where Humphreys kind of gets the idea of doing the stuff he does in his proof. And so the idea really is fundamentally creating new representations from old ones. And so we looked at representations in an earlier video, and what I'll do is I'll put this video right after that one, and then we'll move, well, that was in section 2, and then we'll move from back into section 3 and then knock out the proof for Engel's theorem. So that being said, recall what a representation was. It was simply this vector space homomorphism pair. So we said representation of L in V was this homomorphism from L into the general linear algebra of V. And so this naturally gives the notion of acting on V, because we take an element of L, we'll call it X, and for the rest of this video, if I don't explicitly say it, X will represent an element of L. So X is an element of L, and then phi of X is a linear transformation that acts on vectors in V. So what we can have is this notation x dot v, which is what Humphreys used it, but you might see other notation. And this is congruent to saying phi of x times v for some vector v in the vector space. And so I'll try to make the v's when they represent the vector space big, and the small v's to represent vectors in that. But I'm not sure how well I'll do with that. So this is a representation, and we looked at the adjoint representation, add, which was a representation of L in L. So it sends vectors to the general linear algebra of L. And so this guy here is a Lie algebra, or rather, it's obviously Lie algebra, but we're viewing it as a Lie algebra, as opposed to here, we're kind of viewing it as a vector space. And so that is the adjoint representation, and I guess we can just move on to the new concepts. So the first thing I want to talk about was the direct sum of representations. So let phi1 be a representation of L in vector space 1, which I'll denote V1, and similarly let phi2 be the representation of L in vector space 2. So we can construct a new representation which we can denote as phi1 direct sum phi2, and the way it acts on vectors in L is the same as the direct sum of the individual matrices that we get, or, well, matrix if we fix a basis, but really it's this direct sum of these linear transformations, of the individual linear transformations. So this guy's we know this guy because we know phi1, and we know this guy because we have phi2, and so we just create the direct sum of them. And so phi1 kind of acts on vectors in V1, and phi2 acts on vectors in V2. So overall, phi1 direct sum phi2 is a representation of L in V1 direct sum V2. So this is a pretty straightforward concept that we'll use later on, but not for Engel's theorem, but I'll just mention it anyways. The next thing is a sub-representation. This is a very important concept. And so the sub-representation kind of is relative to a representation. So let's say we had phi is our representation of L in some vector space V. Now suppose V has a subspace called W with the additional property as follows. So let me draw a picture for clarity, and I'll actually change the color too. So we have V here, and then we have W is the subspace in V. And so suppose phi is a homomorphism such that whenever you take vectors in L and you act on W, so we'll use lowercase w, we always end up with something back in W. So that is to say, for all x in L and for all W in W. So somehow W is invariant under the action of L. So that is like if we just ignored V, we would never actually leave W even with this homomorphism. So phi goes from L into the GL of W. What we can do is we can consider the new representation. We change colors again. Phi sub W of well, of L into GL of W. And so what we're really doing is, so like let's say V is 10-dimensional and W is 5-dimensional. We're just saying zoom in on W, ignore everything in V, and we'll just consider this sub-representation. And so it's a very straightforward concept. I think perhaps an elucidating example might be going back to the adjoint representation. So the adjoint representation, right, goes from L into general linear algebra of L. So what we're doing is we have L here, and so this is as a vector space, and then L acts on itself as this set of linear transformations. But suppose we had an ideal living in L, so we'll call that I, right? And ideals are very friendly with the adjoint representation because we know that if you take some vector in L and then you adjoint it with a vector in I, you're going to get another vector in I. So what that lets us say is add of x acting on I is an element of I for all x in L and for all I in I. So if you look closely, this kind of looks like this guy up here. And so what we can do is we can kind of consider the sub-representation where we just zoom in on general linear algebra of I. So that is a pretty straightforward example. So that is a sub-representation. Now let's move on to why I really wanted to make this video, which is the factor representation. And this will be used in the proof. So once again, this is constructing a new representation from one we already know. So suppose we had phi is a vector space, rather it's a representation of a vector space V, or of L in V, so nothing new. And suppose we had a vector space W as before, like this subspace of W, of V. So V is a subspace of V, and we have phi of W, or nope, phi of X acting on W is always an element of W. Subspace. So we have this stuff as before. We can consider a new vector space constructed from V and W, which is the quotient space. So V quotient out W. And this is defined similarly in terms of cosets, excuse me. And so we have the following. Right, we just take V, each vector in V, and add it to W, and we get a coset. And then the set of all these cosets is the quotient space. We talked about a quotient algebra. Obviously, this is not a Lie algebra because there's no notion of a bracket or anything. So we do have a quotient space, though. And so what we can do is we can consider the factor representation in the quotient space, and that's going to be phi V quotient W. And this sends vectors in L into the general linear algebra of V over W. So this is the factor representation. So clearly it depends on your homomorphism, it depends on V, and it depends on W. And the way it's defined is pretty simple, right? So what we're saying is what we need is phi V over W is going to take vectors in L, and then it's going to act on vectors in V quotient W. So this is kind of a linear transformation, and then it's going to act on vectors in W, so V plus W. And we're going to define this to be, we're going to basically use this representation we already have, which is why they're related. And we're going to say this is phi of X, which is an element of this guy, the general linear algebra of V. And so that means he can act on V. And then we're going to add him to W. So as you can clearly see, this is an element of our quotient space. And this is also an element of our quotient space. So it's a little bit confusing, right? But all we're doing is we're saying, okay, I want to act on this quotient space, and I want to naturally extend it from the representation I already have. So each element of the quotient space up to a difference, right? So V minus V prime element of W is equivalent to V plus W equaling V prime plus W. We talked about that in an earlier video. And so up to a difference, we have these cosets in W. And so I can just take my homomorphism I already have, act on V, and I can define that as my factor representation. So that's actually it for this video. It's a short video, but I felt that these concepts were pretty important before we could look at Engel's theorem. So thank you for watching. I will see you soon, I guess.